I'll be presenting as a title notes is on the City of Toronto's wet weather flow master plan. The plan in and of itself dealt with urban non-point source pollution and runoff in its entirety. Focus of today's presentation is going to be on the water quality component. There's a separate presentation dealing with the urban runoff from an urban flooding standpoint. We've updated the plan recently to deal with these extreme storms that we've had in the city that have occurred far more frequently. And we have now, as part of the City of Toronto's climate change adaptation strategy, a very comprehensive program to deal with urban flooding. So, presentation overview, I'll give you a little bit of background in terms of what we were dealing with the City of Toronto, how we developed the plan, the elements of the plan, and then a few concluding comments. So, Toronto, as shown on this slide, is located on one of the Great Lakes, Lake Ontario. We are the largest city in the country, population of 2.8 million. Fairly large area for an urban center in Canada, as you heard from Banu's presentation yesterday. We're the largest urban center, 640 square kilometers. We're blessed with a very long waterfront area along Lake Ontario, and along that waterfront we have 11 waterfront beaches, which the city is quite proud of. Need to pause here for a minute from the standpoint that while we're blessed as being located on one of the cleanest freshwater resources in the world, we do have our own problems. So this is a satellite image of the Lake Ontario basin, the western basin, and you'll see the hard surface area represented by the black in amongst the green outside. So while City of Toronto's population is 2.8 million, we are located in an area where, when you take into consideration the suburban areas around Toronto, it's almost double that. It's just shy of 5.7 million residents. So in terms of the city's sewer system, this is the lay of the land. The central core, which is the oldest part of the city, is serviced by combined sewers. And combined sewer, we've got sanitary sewage as well as stormwater runoff, typically from road drainage collected in a single sewer system. And then we have hydraulic relief structures called combined sewer overflows, so to help prevent flooding, particularly of the sewage plant downstream, called combined sewer overflows. You'll hear me refer to them as CSOs. The rest of the area outside of the pink area is separated by separate sewer systems, separate wastewater collection system to a road drainage collection system, storm sewers. We have 6 watersheds that cut across the city, and all but one of those watersheds extend well beyond the city limits. And in terms of a sewer infrastructure, we have over 10,000 kilometers of sewer infrastructure. The point that I need to emphasize here is that we're a fairly old city, where some of that sewer system goes back to the mid-1800s. About 20% of our sanitary and combined sewer system is over 80 years of age. So theoretically, it's beyond its service life. City of Toronto has made a concerted effort to renew its aging infrastructure, particularly on the water and wastewater side. And we've made a concerted effort to chip away at our infrastructure renewal backlog. I need to come back to the point that Catherine raised yesterday, and I can't overstate how important it was, decisions that have been made in evolving our organization, where the management of water, wastewater, drinking water, stormwater, combined sewer overflows is all under one organizational structure. It's been extremely helpful for us because it's truly looking at urban water management in an integrated way. I also want to make reference that everything that you're going to see in my presentation today and everything that we do in Toronto that is wet is paid for through the sale of water. So you saw Banu's presentation yesterday. In Toronto, the cost of water is $3.20 per cubic meter, translates to current exchange rates in America is about $2.40 US per cubic meter. And we've been benefiting from the standpoint of having raised water rates for 9 consecutive years, 9% per year, to generate the kind of revenue that's necessary to invest in our backlog, to invest in water quality objectives, as you're going to see, and as well as dealing with urban flooding. This is, as Henry noted in presentations, you need to know what it is that you're dealing with in terms of sources of pollution. And in our case, this is the lay of the land so far as concentrations that were measured in Toronto sewers over an extended period of time, both in terms of stormwater and combined sewer overflows. The little triangles you see are the provincial water quality objective for the protection of aquatic life, save for the right side, which is E. coli, and that's for the protection of public health, and it's the recreational beach water quality standard. So let me deal with its general constituents. The take-home message there is that water quality concentrations in stormwater and CSOs are similar, and they're typically 1 to 2 orders of magnitude higher than the provincial water quality objective. When it comes to E. coli, stormwater is typically about 3 orders of magnitude, and combined sewer overflows are typically 3 to 4 orders of magnitude higher than our provincial water quality objective. I also need to reference that I think it's recognized internationally that 100 counts of E. coli per 100 milliliters is a fairly stringent recreational water quality objective. The national standard for us in Canada is 200. This is a slide showing a major discharge. This is the Humber River. It's the biggest watershed that cuts through the city. And the point of this slide, this is an extreme storm event. It was a 1 in 50 year return storm. And what you're seeing, quite clearly, it's the turbidity and the flow demonstrating it's a good tracer, a good marker in terms of the pollution impact that a major storm can have across our waterfront. It just so happens that down in this area is one of our prized beaches, was one of our prized beaches called Sunnyside Beach. But the point of this slide, I want to emphasize a couple of things. One is Lake Ontario is a very dynamic water body. Lake circulation could be east tending, west tending, and it could change within the course of a day. Mild currents to very extreme currents, and as well during the summertime, the lake stratifies. And it's really, from a pollution standpoint, a worst case scenario, because any pollution impacts to the near shore area of Lake Ontario typically are confined to that epilimnium area, the top surface layer. And so it's a worst case scenario so far as trying to, in regards to impacts on our recreational waters. So fast forward, 1987, the International Joint Commission, this is the agency that has carriage of water issues binational US and Canada, identified Toronto as one of 43 polluted areas of concern. So we've got this dubious distinction of being one of the more polluted water bodies, areas within the Great Lakes Basin. And largely, the impaired beneficial uses, as defined by the International Joint Commission, were attributed to discharges from our combined sewer overflows and our storm sewers. And you'll see the impacts that have been identified here, but perhaps the impact that has caused the greatest concern and driven most of the action is this, and that's the impact on beach water quality. Our beaches located across the waterfront, as I noted, there are 11, and the city is quite proud of them. Not so proud when we had some really serious beach water quality problems, but we have seen significant improvements over time. As well, just as I noted, I'm not going to dwell on this, but these are the physical impacts associated with flooding. These water courses that cut through the city are still adjusting to the impacts of urbanization, and as a result of that, there's downcutting of the stream valleys. And in the stream valleys, we typically run, this is the low-lying areas, we have a gravity-run collection system, and that's where we've got our trunk sanitary sewer. So the bottom right is a trunk sanitary sewer exposed just after a major storm condition, and that's a huge issue of concern for us, both first and foremost from a water quality standpoint, human health standpoint, and then secondly from an infrastructure protection and service delivery. So the Wet Weather Flow Master Plan, just to conclude, we identify wet weather flows as discharges from combined sewer overflows, stormwater discharge, and then infiltration inflow into our sanitary collection system. We followed a class environmental assessment process, and in the province of Ontario, that means it's very prescribed. You need to identify first and foremost, what are your end objectives from a receiving water standpoint? What do you hope to achieve? What options are there to help to achieve that end objective, and you need to assess those options. And you establish criteria, one of which is cost, but there's other considerations with respect to impact, the social or the economic component as well. And then you have to involve the public in the decision-making process to end up with a final plan. And in this particular case, we were guided by a steering committee made up of city staff as well as councillors and representatives from the public. Set up our objectives, again, to begin, they're categorized, I'm not going to get into them, but water quality being the key one, water quantity, natural areas and wildlife, and again, talking about our stream corridors and then our sewer system. So from a target setting standpoint, that was one of the first things that we did. What was the level of improvement that we expected to see in our receiving water? And then to help guide the process, because we had some really good data, sewer system data, stream data, we relied heavily on computer simulation modeling. So we used the US EPA HSPF model to model the watershed inputs, the stormwater inputs into the watershed, looking at in-stream concentrations and flows. Looked at the Dorsch QQS model for our combined sewer system because it's an awfully complicated system from a hydraulic standpoint, and to be able to identify what those CSO volumes were, we relied on this hydraulic model. And then ultimately, all of these inputs were fed to a lake-based model. This is the DHI Mike 3D. And in the province of Ontario, dealing with the combined sewer overflows, the province, the regulator, wants you to assess these options and to develop a plan that's based on an average year, average rainfall characteristics. There was an awful lot of work done to develop that and to define what that average year was. So, and then ultimately, once the models are set up, the good thing is that you've got a fairly effective way of assessing the what-if scenarios. What if I did this versus that? And then ultimately looking at what the expected receiving water impacts were going to be. Okay, so just to give you a sense in... stop. Okay, so to give you a sense in terms of what we're looking at, this is output from our computer simulation model. This is the DHI Mike 3D model. So this is what you see here is a blob coming out of, so first and foremost, this green area is the landmass, this purple area is the lake, this red blob is coming out of the Humber River. When I showed that turbidity plume, that's akin to the turbidity plume coming out of the Humber River. And this is another creek down at the west end. So this is a small stretch of the western waterfront of the City of Toronto. What is represented here are isoplests of E. coli concentrations, and as the simulation goes on, you're going to see that the sewers will kick in at some point through the storm when we've got higher intensity. And so what this will show you is the dynamic conditions under which we're having to deal with, and the fact that a steady state condition doesn't work in terms of assessing control options. On the bottom, you'll see the vectors showing lake circulation for the period during the storm. Again, I just want to show you just what happens. Now you see that plume that was originally tending east is now tending west. It's now merging with the plumes from the small sewers, relatively small sewers across that stretch of waterfront. So that's, again, the advantage of the model was really for us then to look at what-if scenarios in the assessment of different options that were under consideration. So fast forward. We used a watershed-based approach. So as I noted, so the colored areas really represent these are all the watersheds, the 6 watersheds, and the City of Toronto contribution of the watersheds is the colored area at the downstream end. As I noted earlier on, all but one of those watersheds extend across the city. So in developing this process, we actually had to account for the inputs upstream of the city. We had to account for further urbanization in urban centers outside the city while taking into consideration continued urbanization within the city. We had 5 consultants, engineering consultants. Each one of them parsed out a component of the watershed analysis, which all then fed into the 6th consultant that did the lake circulation modeling at the downstream end. We used a hierarchical approach, meaning we took a look at what you could achieve in individual lot parcels, followed by the conveyance system, which is under municipal operation. This is our sewer system. And then ultimately what we couldn't control in those 2 areas, we had to deal with at the end of the system, the end of pipe. So watershed-based approach recognized that whatever we do on an individual lot parcel, once you scale it across the neighborhood, you scale it at the sub-watershed level, ultimately there's a net impact and improvement at the watershed scale. And again, in this particular case, the Humber River watershed, which is the biggest watershed, we only represent the City of Toronto, about 15% of the total drainage area. This is a series of strategies that we developed. Just on the left side, you'll see that we named them based on what it is that we were expecting to achieve. So we went from the status quo meaning that what would happen with continued urbanization in the city, because it's it wouldn't be the same as it is today. Opportunistic would mean that over the course of 25 or 30 years, if we took opportunities that presented themselves, what could we achieve? And then scaling over to number 5, which is really aggressive, looking at an enhanced level of water quality objective achievement at the end of the process. So again, 5 strategies. So this is representative. We took an assessment based on terms of what we expected, based on the modeling results from a water quality standpoint as well as costs, and we came up with these curves, which basically strategy 1 through to strategy 5. Take-home message here is strategy 5 scores the highest, but it comes at a cost. It's the cost premium. That notwithstanding, the public as well as our council really directed us to achieve ultimately for that end objective. We won't get there overnight, but basically to head in that direction. So we develop a master plan with 25 years worth of projects, and then ultimately looking at prioritizing the projects, first and foremost being health and safety. SARS controls, this is huge for us in terms of educating the public that they themselves or the property that they own contributes to the problem. There are things that they can do on their individual properties to help reduce the impact of wet weather flow. We pushed the envelope on the downspout disconnection because the roof areas were all connected to the sewer system. If not to the storm sewer system, they were connected to the combined system, and there's a volume of runoff that didn't need to be in our sewer system because ultimately we'd have to treat it downstream. So we had a voluntary program where we provided rain barrels to the public, and the uptake was nominal. So then we pushed the envelope, very aggressive, and we mandated the disconnection of the roof downspouts as per the timelines noted here. So by the end of 2016, we will have all of the roof downspouts, about 350,000 houses impacted. We also developed guidelines to basically, if you were developing now in the city, if you were redeveloping parcels of land, the status quo was no longer acceptable. You had to put in place stormwater controls on site. And so we developed our wet weather flow guidelines. The map on the bottom right, the green areas represent areas of the city where the city planners have proposed further intensification and urbanization. And so those are opportunities for us for enhanced stormwater controls. These are the numeric values. We've got water quality and water quantity control. On the bottom, I just want to draw to your attention the fact that we've prescribed a minimum level of runoff control. And so if you're developing the downtown core, you don't have space to do much of anything. But you do have an opportunity to collect that rainwater into a cistern, pump that water out to flush toilets, urinals, or landscape features, and many developers are doing that. Conveyance, this is where it's a municipal responsibility. On the top left, we have about 20% of the city is serviced by ditch roads, and our challenge is to maintain that configuration. There are other examples shown on this slide where we're looking at leaky pipes to basically infiltrate the stormwater, providing some level of treatment, filtration, before it's actually infiltrated into the ground. Here's another example where we've used heavy-duty plastic crates within the road boulevard area that provide storage for stormwater and infiltration opportunities, while at the same time promoting healthier trees, particularly in the densely populated areas. In this particular slide, we took all of the engineering borehole records together and we mapped out areas of the city that have sandy soils because it's not very homogeneous, and the orange represent areas that, as we renew our aging infrastructure, provides us an opportunity to put in these leaky pipe systems. Stream restoration. We have about 370 kilometers of stream, and we often overlook the importance of those streams. We typically look at them as open channels for the conveyance of stormwater. Well, in our case, we've prized ourselves of those channels, and we've typically used a natural channel design approach to maintain and enhance those systems. Taking a dilapidated, heavily eroded area and now looking at natural channel design principles to reconfigure that channel, basically ultimately trying to mimic Mother Nature, trying to configure that channel in terms of what this new flow regime through urbanization wants to take it, and then recognize that over time there will be some adaptive management. The stream will want to move within limits, and we plan for that. And so here's the map showing the stream restoration work across the city in terms of the reds. Then what we can't do at source or conveyance is ultimately end of pipe, and different examples. Stormwater pond on the bottom left is an embayment that we took up using pontoons and plastic curtains floating off the pontoons to compartmentalize that embayment so that we provide stormwater treatment. Infiltration basin at the bottom center, and there's a soccer pitch right over top of that stormwater management feature. And then more aggressive civil infrastructure is these underground storage systems. Here's an example of a recently completed pond. This is right in the heart of the city. Need to emphasize that all that you're going to see is basically retrofit within an existing urbanized area. So we're quite proud of this one. It's the largest facility of its kind in southern Ontario. The neat thing here is we're drawing stormwater out of the facility to augment the irrigation needs of a local golf course. And in the wintertime, because it snows in Toronto, we have a local ski hill, and we're using stormwater, which apparently makes just fabulous snowmaking source because of the impurities in it for the local ski hill. So here's the lay of the land, 173 green facilities, and where we were space constrained, particularly in the downtown core, had to bite the bullet and go underground with underground storage systems. I apologize for the quality, but we're going to talk about this underground storage system in a minute. Which leads me to this. Henry, I think I'm over time, but if you just beg your indulgence for a few minutes. The Don River is recognized across Canada as one of the most polluted rivers in the nation. And it was a long history of problems. And it flows into this inner harbor, and this was really the genesis of Toronto being identified as a polluted area of concern. The Don River, just to give you a sense, back in the 1970s, graduate students from the University of Toronto, mocking the death of the Don River because of its water quality, had a funeral, a mock funeral through the University of Toronto campus. So we've had a long history with water quality problems. Lay of the land for the Don River is the downstream end, the lower Don River. It's impacted by combined sewer overflows in addition to stormwater. So in accordance with the provincial requirements for combined sewer overflow control, if you're discharging to a beach area, they prescribe that the control should be that for a typical year, you should only overflow 1 or 2 times per typical year. If you're discharging to a harbor area, as we are here, they prescribe a much lower level of control, which is 90%, which translates to 10 to 12 overflows per summer season. Well, in Toronto, public politicians pushed to the 1 overflow, akin to if it were a beach area, and that's the level of control that we're providing. Bottom line, here's a series of tunnels picking up all those combined sewer overflows, very extensive system providing 570,000 cubic meters of storage, and then ultimately flowing to a downstream facility that we will construct providing high-rate treatment with UV disinfection. This is a representation. We have one of these systems at a much smaller scale along one stretch of shoreline. These are massive facilities, typically about 50 meters deep and 30 meters in diameter, these storage silos connected with a 3-meter diameter tunnel. High-rate treatment, we've spent a decade plus working with our colleagues at Environment Canada and the Province of Ontario Ministry of the Environment to look at high-rate treatment for combined sewer overflows. We went from pilot scale to full-scale demonstration, and now we're completely retrofitting an existing combined sewer overflow storage tank, adding cationic polymer to enhance primary treatment to provide, in the measurements that we've done and in the analysis that we've done to date, 70% solids removal, which is huge. The advantage here is you can see by the flow rates that we can push through the system, a much smaller footprint is required to push much larger volumes of flow, which is what we're going to need with this massive storage system that we have proposed. Finally, in terms of the lay of the land, this is a slide which basically integrates all of what we expect to achieve. So the gray represents the landmass of Toronto looking north. This is the island. This is this inner harbor where the Don River flows. And the colors represent isoplex of E. coli. So the pink represents conditions across the waterfront over the Annam, where E. coli concentrations, 10% of the time, would be in exceedance of the 100 counts per 100 milliliter. And the blue represents where they would the concentrations 25% of the time and more would exceed the 100 counts. So final thoughts: leadership and support across the city departments, collaboration with the approving agencies is required, public education, I can't emphasize that enough, and there's no one solution. Multidisciplinary, multifaceted approach is required, adaptive management wherever we can, And most importantly is the last, and that seize opportunities to integrate controls. So new urban development, for those of you that have new urban development, you have an opportunity to do it right, learn from the mistakes like we have in Toronto, done in Toronto, and infrastructure renewal provides us an opportunity to shoehorn in the fix over time. So ultimately, this is what we like to see. This is a picture taken in that beach that I mentioned early in my slide. And somebody in the office said it looks like an engineer's day at the beach where, you know, we're dressed in our suits and ties. But ultimately, we would like to draw the public back to the beaches that they've been so fond of. And I can't finish the presentation without acknowledging a tremendous level of effort behind the scenes to put all this together. So with that, I want to thank you. Thank you for your attention.